We are going to be looking at redox reactions in this video. And this name may sound a little bit unfamiliar to you right now, but you have actually seen or you know of some reactions that happen around you that are redox reactions. So one very common example is that of rusting. And you would have seen rusting in cars or on your bicycles that look something like this. And rusting is a good example of a redox reaction. Another example that you may be aware of is photosynthesis, which is also a redox reaction. Then there is also combustion of fuels like methane, which again is an example of a redox reaction. So you have seen many of these redox reactions around you. But then the question is, what are these redox reactions? And there is a clue in the name itself. Redox reactions are essentially reduction and oxidation reactions. So the word redox tells us that in these reactions, there is oxidation and reduction taking place. And we know from before what oxidation and reduction are. Oxidation is the loss of electrons and reduction is the gain of electrons. So redox reactions are those reactions in which some species undergo oxidation, whereas others undergo reduction. Or in other words, we can say that some species lose electrons while others gain electrons. So let's take an example and understand this better. So as we saw, let's say in a redox reaction, some species undergo oxidation and some species undergo reduction. But then how do we keep track of which species have lost electrons and which species have gained electrons? So for that, we use oxidation numbers, which is an idea that we use to keep track of electrons in reactions. So there are some rules used to determine the oxidation numbers of chemical species in a reaction. Let's discuss some of them. So the first one is that the oxidation number of a free species is going to be 0. So if you have pure iron taking part in a reaction, in that case, its oxidation number will be 0. Similarly, if you have chlorine gas or hydrogen gas that is taking part in a reaction, in each of these molecules, each chlorine will have an oxidation number of 0. The same goes for the hydrogen here. So the idea is, if there is a free species in the reaction, its oxidation number is going to be 0. Next, if we have monoatomic species, like let's say this sodium or this bromine, the oxidation numbers in both of these cases will be equal to the charge on these atoms. So we know that in the case of sodium, it loses an electron to get to a charge of +1. So the oxidation state of sodium is +1. Similarly, in the case of bromine, in reactions usually it will gain electrons. So the charge on bromine in those cases is -1. And so the oxidation number of bromine is -1. Now it's not necessary that a given species has only one oxidation number. It could have different oxidation numbers depending on what compound it forms. So for example, if we consider hydrogen, in most of the compounds that it forms, it will have an oxidation number of +1. And similarly, in the case of oxygen, the most common oxidation number it has is -2. Sometimes if the oxygen that we are considering is forming a peroxide, let's say hydrogen peroxide, it can have an oxidation number of -1 as well. But the most common oxidation state that we see is -2. Another one is fluorine, which has an oxidation number of -1. And assigning oxidation numbers of hydrogen, oxygen, and fluorine is usually the starting point in calculating oxidation numbers of the other species. Another rule that we have in case of oxidation numbers is that for a neutral compound, the sum of oxidation numbers of the atoms will be equal to 0. So like let's take the case of this HNO3 here. Now from what we saw before, let's say that we know that the oxidation number of hydrogen is +1. And for each atom of oxygen, the oxidation number is -2. So let's say we want to find the oxidation number of this nitrogen. So we know that the sum of oxidation numbers of all the species in this neutral compound is going to be 0. So we know that the oxidation number of hydrogen plus the oxidation number for nitrogen plus the oxidation number for 3 atoms of oxygen is going to be 0. So we know that for hydrogen, the oxidation number is +1. Let's say the oxidation number of nitrogen is X. And we know that for oxygen, the oxidation number is -2. And we know that this sum will be equal to 0. So if we solve for X here, we get X to be 5. So in that way, we can calculate that the oxidation number of nitrogen in this case will be 5. So these were some of the rules and some context for oxidation numbers. Now let's see how we can use this idea of oxidation numbers to find out whether a reaction is a redox reaction or not. So now to see how we can identify whether a reaction is a redox reaction or not, let's take the example of rusting that we saw before. So we know that rusting is a process in which iron undergoes oxidation, forming the reddish colored rust. which is an oxide of iron. So if we were to write a reaction to describe the process of rusting, it would look something like this. Now, usually rust is denoted as Fe2O3.NH2O, where N is a number denoting the number of molecules of hydration. So this could be 2H2O or 3H2O. And that is because for rusting as a process to happen, there is also water involved. But for simplicity, for now, let's just assume that this reaction represents rusting. And we are going to use Fe2O3 to represent rust. So we have iron reacting with oxygen to give this oxide of iron, which is chemical representation of rust. Now, if we look at the oxidation states of iron and oxygen, as we saw before, since both of them are free species, their oxidation numbers are 0. And this is before the reaction takes place. Now, when the product is formed, we know that for oxygen, the common oxidation number is -2. So as we saw here, we know that the sum of the oxidation numbers of iron and oxygen will be 0. So if we take the oxidation state of iron to be X, so we have 2X plus 3 times -2, that is -6, will be equal to 0. So if we solve for X, we get X to be 3. So that means for this iron, the oxidation state is +3. So now if we look at the change in oxidation numbers of both of these as the reaction takes place, we notice that iron goes from an oxidation state of 0 to +3. So that means iron is losing electrons. And similarly, in the case of oxygen, it goes from 0 to -2, which means that oxygen is gaining electrons. Or in other words, we can say that because iron is losing electrons, iron is getting oxidized. And because oxygen is gaining electrons, oxygen is getting reduced. So based on how we define redox reactions, we have oxidation and reduction taking place in this reaction, which is why rusting of iron is a redox reaction.